A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the deformation gradient tensor. So let us get started. So in the lecture today we will start with a discussion on the displacement field and then we'll move on to a discussion on the deformation gradient tensor, which is one of the most important quantities when quantifying deformation in continuum mechanics. So let's get onto it. So let us say this is the body in its reference configuration. And we have a point A, that is a material point A in the reference configuration. And then the body deforms at a later time into a current configuration. And the point A has moved to this small a in the current configuration. So here is our coordinate system, that is O, capital X1, capital X2 and capital X3. And the unit vectors are I1, I2 and I3. So this is the reference coordinate system, and we agreed on the fact that in most cases we'll assume that the spatial coordinate system also overlaps the reference coordinate system. So we'll also write this as comma small x1, comma small x2, comma small x3, and this is comma e1 hat, e2 hat and e3 hat. So then we can write the position vectors for points capital A. So this is capital X A vector, and the position vector for small a is small x A vector. So these are the position vectors for the point A in the reference and the current configurations. Of course, in the reference configuration, I use the material coordinate system, and in the current configuration, I use the spatial coordinate system. And we can see that the point A has displaced. When the motion happened, it displaced from capital A to small a. So we can write its displacement as the vector u with a superscript a, because we're talking about the displacement of the point A or the material point A. From these three vectors, we can see that the vectors capital XA and displacement vector UA add to give the small xa. This is a vector, sorry. And from here, I can find that displacement UA can be written as small xa minus capital XA. So this UA tells us the displacement of the material point A when it goes from the reference to the current configuration. In fact, I can define a displacement field that is simply the vector u, which is small x minus capital X. So you feed in any coordinate capital X for this, and that gives you the displacement of that particle which was denoted by that capital X. So this u, the displacement field, can be expressed in terms of its Lagrangian coordinates. That is, I can specify u as a function of capital X and t. So this becomes the vector small x, which is also expressed as a function of capital X and t, minus the vector capital X. So this we'll call the Lagrangian description. So this expression for u in terms of its Lagrangian coordinates is telling us the displacement of a particle which was at x, because you're specifying everything in terms of x here on the right hand side. Of course, it was in the reference configuration because capital X is defined for the reference configuration. So it's telling us the displacement of a particle which was at capital X at all later times, because you also have time here, time here. So you feed in a capital X and a time, and it tells you the displacement of the particle denoted by this material coordinate at the time specified. So if you have two configurations like this, and this is the particle capital A that went to this particle small a by this displacement, we have information about the material coordinate of the particle. This information is not available. When I say not available, that means it is not readily available when you passed information to the displacement field. Of course, it may be available from the deformation equations, but from the idea of Lagrangian description, what we mean is that we are focused on the displacements of material particles at later times. If the situation demands, we sometimes have to express our displacement field in terms of its Eulerian coordinates. So in that case, we write the displacement field as small x minus capital X, which is a function of small x and time. So this is called the Eulerian description. So this is required when we want to find out the displacement of the particle which is at x, that is small x spatial coordinate, at a time t. So if this is the reference and this is the deformed configuration, then if a point goes to another point small a, then what we have is we have information about this small point a, and we'll want to find out the displacement of where this particle is coming from. So this is sort of known because we know the spatial position, but we do not know where it is coming from. So this is where the Eulerian description of the displacement field becomes more useful. Now please note that displacement is always from the reference configuration, irrespective of how I express my u, that is whether I express it in the Lagrangian or the Eulerian coordinates, it is always from the reference to the current configuration. Now with this definition of the displacement field, I can differentiate that with respect to time. So that gives me d small x by dt minus d capital X by dt. But we know that d capital X by dt is a 0 because capital X's are defined in such a way that they are independent of time. So this simply becomes d small x by dt, which is nothing but the velocity vector. So we can also express the velocity field as the time rate change of the displacement field u. And similarly, the acceleration field can be written as the second derivative of the displacement field with respect to time. So we will be solving some problems in this week's tutorial to understand this idea better, where we find the velocity and the acceleration fields using the displacement field rather than using the spatial coordinates. So now we move on to the second part of today's lecture, that is on the deformation gradient tensor. So let's say this is our initial configuration and this is the configuration at a later time. So in the discussion that will follow now, we'll only talk about two configurations. So one we'll call undeformed and the other we'll call deformed. So there'll be no effect of time now. We're only interested in two snapshots. One is at the undeformed configuration and the other is at the deformed configuration. All the discussion that follows will only take these two configurations into the picture. So we will get rid of the time for the discussion that will happen now. So we have a point P in the undeformed configuration, and this P denotes a material point, that is some physical material point in the body. And what we're interested in is to understand what happens around P as the body deforms. So if point P goes to small p here, then I would want to understand how I would have a point Q, let's say, which was close to P in the undeformed configuration. Where would it have gone in the deformed configuration? Of course, this point Q is arbitrary. We can move around the point Q and figure out what happens around the material point P as the body deforms. And this will give us an information about what is happening in terms of the specified deformation that is given. So let's write it down. So our interest is, so as we said, our interest is to find out what happens around the material point P as the body deforms. So for reference, let's write our coordinate system as well. So this is the origin. This is capital X1, capital X2, capital X3, and we are again assuming that our spatial and material coordinates coincide. I'll place my point Q a little further. So this is some sort of an exaggerated situation, although in reality the points P and Q are close to each other, because that is what we desire. We want to find out what happens in the neighborhood of point P. But for the sake of drawing diagrams, it's much easier if I put them a little further for clarity. So the position vector for capital P is given as capital XP, and the position vector for small p is small xp. And this green vector, of course, is our displacement vector for the material particle P. Now this is just one point P. But if I have the information about what's happening in the neighborhood of each and every material point, then I basically have the information about the deformation in the whole body. So since the relative position of Q with respect to P requires us to denote this vector, because as Q moves around P, the vector that we have just drawn will change. And this vector that I've just drawn is nothing but the capital X vector, because I can show that to you, that the point Q has a position vector which is capital XQ, and this capital XQ is given as capital XP plus dxp, because all the discussion is happening with respect to the point P. So I can simply write that Q is dx away from P. With that understanding of notation, we also see that in the deformed configuration, this vector from small p to small q is the vector d small x. So that means that I can write the position vector for small q in the deformed configuration as the position vector for P plus the relative displacement between P and Q as d small x. Now remember, our point P is fixed for the discussion, but point Q is moving around point P, because that will allow us to get the information about deformation around the point P. So for every d capital X vector, we will have a corresponding d small x vector. So what that means is, as I move around my capital Q around capital P, I get different positions of small q with respect to small p. So as capital Q moves, small q moves as well. And this mapping from d capital X to d small x gives us that information. So you can see that our aim now is to find d small x as some function of d capital X. So what follows now is going to be some mathematics. So we write d capital X, which is a vector, in its material coordinate representation. So that becomes the components with indices capital A times the unit vectors I hat A's. So when I expand this, this becomes d capital X1, I1 hat, and so on. So dx1, dx2, and dx3 are the three components of the vector dx. Now please remember that if the notation confuses you, then just look at the vector here, and we're just talking about the three components of this vector. Similarly, for the position vector d small x in the deformed configuration, I can write this as d small xi times ei hat. Now this we are expressing in the spatial coordinate system because that is what we do. All the undeformed configurations are written in the material coordinate system and the deformed configurations are written in the spatial coordinate system. So this can be expanded to this. Now please note that although it may be confusing that we are using capital indices and small indices in these two different cases, but the indices A and I, they take values 1, 2, and 3. So although A represents indices in the material coordinate system and I represents indices in the spatial coordinate system, they both will take the values 1, 2, and 3 only. This is just for our notational convenience that we use capital and small indices. Also, as we'll see later, that these capital and small indices will help us identify that if we are doing some differentiation, whether the differentiation is with respect to small x's or capital x's will simply be clarified by the use of small or capital indices. So now we recall our chi function, which was a function which takes in the material coordinates and time and gives us the corresponding spatial coordinates. So this we also represent as small x function of capital X and t. So this is the function that tells us everything about motion. But now we don't have a time because we only have two configurations. So we can simply write this as chi only being a function of capital X. If I write this in the initial notation, I write the ith index of x, and then this becomes xi as a function of, now just to be explicit, I'll write this as capital X1, capital X2, and capital X3. But our interest is not in xi, our interest is in dxi, which is this vector here. So we differentiate this, so this becomes dxi. On the right hand side, you can see xi is a function of capital X1, 2, and 3. So we use the chain rule now. So this becomes partial xi by partial capital X1 times d capital X1 and so on. Or in our initial notation, we can write this as d small xi is partial xi by partial capital X, and you have a d capital X, and the index I use is a capital 1 because it is for the material representation or the material coordinates representation of capital X's, and here you can see there's a summation over the index A. So as you recall, in our tensor calculus, we had written this quantity as xi comma a. So this is more compact representation of dxi in terms of dxa. And now you see the power of using small and capital indices, that this xi comma a clarifies the fact that this is partial by partial capital XA, because capital indices are used for capital X's, and on the top we have a small xi. And since this quantity by itself is a second order tensor, because you have two free indices here, so this is given a name which we call the F tensor with the indices I and A in this case. So we can write d small xi like this as well. And in the symbolic notation, this becomes d small x vector is the F tensor dotted with the d capital X vector. And you can now see that we have successfully written d small x vector as a function of d capital X vector, where the function is simply a dot product between a second order tensor and d capital X. This F has a name, and you may have guessed that F tensor is called the deformation gradient tensor. This is an extremely important quantity, so I'll expect you to understand its definition and also its significance. And with time and practice, we'll solve problems and see different situations of f having different values and understand what kind of deformation it represents. So with experience, you get a feel of looking at f and understanding what the deformation looks like. Let us expand the F tensor and look at its terms. So these are the 9 components of the tensor F. And please remember that F is defined at some point P, some material point, because it was the information of deformation that's happening around a material point P that we started with. So F will be defined at point, and this is a local quantity. And as I go to different material points in my undeformed configuration, I will get, or I may have, different values for the 9 components of the deformation gradient tensor F. So I'll write the fact that F at point P, it contains information about the deformation around P, because it is telling us that as I move my point Q, which is in the neighborhood of point P, what happens to point Q in the deformed configuration. So I'll write the expression again, that d small x is f dotted with a d capital X, and this if was the point P and this was the point Q in the neighborhood. So we had defined d capital X like this. Now of course you can move capital Q and get different d capital X vectors. So this is some arbitrary choice for Q, and what I'll do now is, to understand, I'll pivot the body at point P. So what it means is that small p also coincides with capital P, but small q, of course, will be somewhere else, which is here, let's say. So this is our d small x. So basically what we are seeing is that since the discussion is relative to capital point P, so I hypothetically fix my body at the point P and see how small q is different from capital Q. So that gives me the relative orientation of d capital X and d small x. So we see here that when we go from P capital Q to small pq, the length small pq may change. In the figure it looks slightly elongated, and the orientation or the vector may rotate as well. As it is done in this case by rotating clockwise. And this is exactly what deformation means. So deformation is with respect to a material point, how the points around it will change their position. Please note that the information about translation is missing in the deformation gradient tensor because we are taking the derivatives of small x and capital X. So if my body simply translates, that means that its coordinates x1 will be capital X1 plus some constant, x2 will be capital X2 plus some other constant and so on. Then if I differentiate this, then this information will be gone. And we have constructed this capital F, rightly so, because it's called a deformation gradient tensor. We are not interested in how the body moves as a whole. We're interested in what is happening to the body in terms of it changing its shape or orientation. So that is the reason we get rid of the translation information by not looking at the position vectors, but looking at derivatives of that. That is by looking at what's happening in the neighborhood of material point P. Now I keep saying material point P, but of course this F is a field, and this deformation gradient field contains information about deformation in the whole body because F is a function of capital X in this case. So as I put different material coordinates for different material particles, I get the deformation gradient tensor for all those material particles. What that means is it tells us the information about deformation around every particle in the body. So till now we talked about finding d small x from d capital X, but of course an inverse transformation is also possible. That is to say that if we have d small x available, can we find the d capital X from that? So for that we write capital X as a function of small x, which is what we call the chi-inverse function, and then we differentiate that. So I'll write this as d capital X A is partial capital X A upon partial xi times d small xi. This we can also write as capital X A comma I times d small xi. So this tensor that we have got here is actually the inverse of the deformation gradient tensor that we just got. So let's say this tensor is G, which is given as capital X A comma I, or I can write this as partial capital X A upon partial small xi tensor. And what I'll do is I will multiply this G with the F that we had and see what we get. So this is the dot between G and F. And if I take just first row of this and first column of this to see what's the resultant 1 1 component, so what we'll see is this becomes, so let's call this H. So H11 is this, and this is nothing but partial capital X1 by partial capital X1. And the way we see that is that if we write capital X1 as a function of small x1, small x2 and small x3, then if I differentiate that partially with respect to capital X1, this becomes, using chain rule, partial capital X1 by partial small x1 times partial small x1 by partial capital X1 plus the other terms. So please don't cancel the terms, see the chain rule here. And this is equal to 1. And similarly, you can find the other components of H and you will see that the H tensor comes out to be identity tensor. So which means that G and F are inverses of each other. So I'll summarize that capital X A comma I is nothing but F inverse. Now this deformation gradient tensor F can either be homogeneous or non-homogeneous. Now, the meaning of homogeneous is something that does not change with spatial position. So F being homogeneous means that the deformation is the same for all material particles in the body. So all material particles deform in a similar way. So if there's rotation happening, then the rotation is the same for all material particles in the undeformed configuration. And if there is a stretching happening, that is also the same for all material particles in the undeformed configuration. So mathematically speaking, we can say that the elements of F do not depend on x coordinates. And then in contrast, non-homogeneous means that the elements of F will depend on x, and this is what gives rise to the more interesting aspects of deformation, where different particles in the body behave in a different way in terms of deformation. So when I say deformation, it's basically what's happening around the different particles. So if you take tiny elements inside the body, they may get deformed differently as you move around in the body. Now there's sometimes a confusion that why have we defined F? Because F is defined from my small x as a function of capital X. So this basically is coming from chi. If I give you a chi, you find the F from that. So this does not contain any new information. If I have the motion equations, that is, if I have small x in terms of capital X, I can find F. But the components of F give a more usable information in terms of deformation. I cannot look at my chi function visually and see what kind of deformation it is very quickly. But I can look at F components and easily figure out what is the deformation happening in the body. And that is the reason this quantity is called deformation gradient tensor, because it has information about the deformation in the body. And that is what we'll be doing in this module on kinematics, that we'll be defining tensors. Particularly, we're going towards the strain tensor or the strain rate tensor, which are all derived from the equations of motion. But when we look at them, they provide ready information for deformation. Now, the aim of today's lecture was to give you an understanding of the definition of the deformation gradient tensor. We do not want to overload you with examples and problems, which are also necessary to explain what F tensor will correspond to what kind of deformation. Because one has to get some sort of a mathematical or a physical feel for the deformation tensor as well. And that will only happen through exercises and problems. And over the next 2 weeks, we will gradually be doing some problems which will help us understand what different types of deformation gradient tensor components correspond to different kinds of deformation in the geometrical space. So thank you very much, and I'll see you in the next lecture.